This demo video focuses on SIRIUS, a new dual symmetric interactive projection technique for high-dimensional data. This technique enables simultaneous exploration of both the observations and the attributes of high-dimensional data. We implemented SIRIUS using 6 mathematical formulas. Equations 1 and 2 define WMDS projections of observations and attributes respectively. Equations 3 and 4 enable projection interactions in each of these projections. Equations 5 and 6 relate observation importances to attribute importances and vice versa. It is these formulas that calculate importance values and their use in initializing the projections, parametric interactions, labeled pi, and projection interactions, labeled pri, that enable this simultaneous exploration and generation of insights for both the observations and the attributes of high-dimensional data. To exemplify how this implementation works, we first use the animal dataset by Lampert et al., which contains a total of 49 animals and 72 attributes for each animal. Displayed here is the initial projection of this dataset using SIRIUS. In this initial projection, more water-dwelling animals appear in the lower left of the observation projection, whereas more land-dwelling animals appear in the upper right. However, looking at the node sizes and opacities in the attribute panel indicate that quadrupedal is actually the attribute that best describes or more greatly distinguishes animals in the projection. That is, rather than animals being separated by their water attribute or a similar attribute, animals are actually distinguished more by their quadrupedal attribute. Since this is the initial projection of the attributes, this also means that quadrupedal is the attribute that many animals have a high value for. This can be interpreted as many animals in the dataset being quadrupedal, and that this attribute is the most popular attribute in the dataset. In other words, more animals have a high value for this attribute than for any other attribute. Furthermore, the projection of attributes showed that there are strong correlations between certain attributes, such as quadrupedal and walks, since they are projected closely together. Similarly, other attributes such as hunter and stalker are also correlated with each other since they are also projected closely together. However, these two attributes are projected farther apart from quadrupedal and walks, meaning that they are not correlated with these other two attributes. If an analyst is interested in a particular observation or attribute, an importance slider is available by double-clicking that node. Manipulating the slider allows the analyst to express his or her notion of importance for that observation or attribute, and is how parametric interactions are accomplished in this implementation of SIRIUS. For example, if an analyst wishes to differentiate animals based on their water attribute, the importance slider for the water attribute can be dragged up. This interaction results in the desired projection of animals, as well as a new projection of the attributes that reflects which attributes are correlated with water, such as swims. To clearly demonstrate how projection interactions work in our implementation, we turn to a subset of the animal dataset to improve clarity. This subset contains 13 animals and 13 attributes. For this example, assume that an analyst wants to answer 3 questions about this subset of data. 1. What attributes separate the tiger and wolf from the blue whale and dolphin, as well as from the cow and sheep? 2. What other animals are similar to these 3 groups? 3. What other attributes are correlated with the attributes that separate these 3 groups? Projection interactions allow analysts to directly manipulate the projection itself to express desired similarities and dissimilarities between a specified subset of nodes. This means that the animals in question can be separated and new insights gained by dragging dolphin and blue whale onto one side of the projection, tiger and wolf into an opposing corner, and cow and sheep apart from either of these 2 groups. When the Update Layout button is clicked, This triggers a calculation of the attribute weights that would produce the same relative pairwise distances between all 6 moved nodes, ignoring all other nodes for now. Once the attribute weights have been determined, all observations can be reprojected. However, the addition of the observation importance calculation enables us to recalculate a set of observation weights and thus reproject the attributes as well. In this new projection, the analyst is able to use node position, size, and opacity to actually answer all 3 posed questions. The first question regarding which attributes separate the 3 groups of animals is answered by the node sizes and opacities in the attribute panel. The larger and darker water, hunter, and grazer indicate that these attributes have the highest weights or highest levels of importance and thus best describe the differences between the animals in the observation projection. This answers the first question completely. The second question regarding which other animals are similar to those in the 3 defined groups can be answered by observing the relative positions of the nodes in the observation panel. Since a WMDS projection places more similar animals closer together, we can see that horse, deer, elephant, and squirrel are most similar to the cow and sheep. Similarly, the Siamese cat and German shepherd are most similar to the wolf and tiger. And lastly, the otter is most similar to the dolphin and blue whale. This answers the second question posed on this dataset. The third and final question is what sets SIRIUS apart from existing techniques. To determine which attributes are correlated with the attributes that separate the 3 groups of animals, we can use the relative position of the nodes in the attribute panel. Since the attribute panel was updated based on changes to the observation panel, the new projection of the attributes accurately reflects the attribute correlations by projecting correlated attributes closer together. Thus, we can see that attributes like forager, spots, stripes, and walks are more correlated with grazer than they are with hunter or water. Similarly, the attributes furry, active, speed, smart, strength, and size are more correlated with hunter than they are with water or grazer. Water, in comparison to hunter or grazer, is not strongly correlated with any other of these attributes. While this answers the third question completely, these answers can actually be related back to the projection of the observations. That is, animals that are high in hunter are also likely to be high in other attributes like furry, active, speed, smart, strength, and size. Similarly, animals that are high in grazer are also likely to have high values for forager, spots, stripes, and walks. However, animals that are high in their water attribute are not as likely as animals that are high in hunter or high in grazer to have high values for any of the other attributes. As an example of how SIRIUS can help analysts explore a text-based dataset, consider a synthetic intelligence analysis dataset, which has had entities extracted and TF-IDF calculations performed on all extracted entities as data preprocessing steps. Displaying this dataset using these TF-IDF values as attributes of the documents, SIRIUS immediately emphasizes Charlottesville as an important entity. Given this is the initial projection, the fact that Charlottesville is highly emphasized indicates that this is the entity that has the highest sum of TF-IDF values across the entire dataset, hinting that there may be something nefarious occurring there. Since Charlottesville is the most important entity, it has the highest weight and therefore the largest influence on the projection of the documents in the observation panel. Thus, the entity Charlottesville separates documents that discuss Charlottesville from documents that do not. Inspecting these Charlottesville documents reveals information concerning several terrorists who are planning their attack from Charlottesville. However, this projection is cluttered, with many observations and attributes overlapping with each other. One way to help with this issue is to perform topic modeling on the data to effectively group attributes together during an additional preprocessing step. Visualizing the topics in place of the extracted entities results in much clearer initial projections. The trade-off in doing so is that the previous initial insight that Charlottesville may be the center of some nefarious activity is lost. To show analysis on text data with SIRIUS, we use the topic model data to improve clarity. A reasonable starting point with a dataset like this is to pick out attributes, in this case topics, that seem more indicative of nefarious activity than others. Examining these topics in the attribute panel uncovers a number of such topics, including one that seems to be about passport information, another about police information, and yet a third regarding explosions. These three topics, in comparison to others such as number, CIA, date, seem to be extremely indicative of nefarious activity. We can perform a projection interaction by dragging the topics of interest into one corner of the projection, and the uninteresting topics into the opposite corner. The projection interaction is completed after Update Layout is clicked. This results in a visualization that shows other topics that are very closely correlated with the three topics of interest that were moved. These new topics, including number report phone and April Avenue report, are also worthy of investigation. However, FBI list number is the most emphasized topic in the attribute panel, which means that this topic best describes the differences in the projection of the documents in the observation panel. It also means that this topic, along with the initial three topics and the two topics that are highly correlated with these initial three topics, is also worthy of further investigation. However, most notably, this interaction resulted in the document FBI 11 being highly emphasized in the observation panel, reflecting its strong association with the emphasized topics in the attribute panel. Double-clicking on this node and reading its contents reveals that two people claiming to be students at the University of Virginia, Mukhtar Galab and Yassin Mosed, are actually not registered students at that school. Furthermore, they both claim to live at a residence in Charlottesville where, in fact, no one lives. The report also gives a potential cell phone number for Galab. This information happens to be central to one of the three main terrorist plots contained within this dataset, as further analysis can confirm. As a final example, we use a breast cancer dataset from the UCI Machine Learning Repository to exemplify how SIRIUS can be used with larger datasets. In this initial projection of the dataset, many observations representing benign tumors naturally group together in the lower left corner of the observation panel, separating themselves from those representing cancerous tumors. Looking at node size and opacity in the attribute panel, we can see that the attributes that describe this separation are bland chromatin and single-cell epithelial size, and, most notably, clump thickness. Thus, an analyst can immediately learn from this initial projection that bland chromatin and single-cell epithelial size do help distinguish between observations, but clump thickness describes the separation between the different observations better than the others. Additionally, since clump thickness is the closest attribute node to class, this means that clump thickness is the attribute that has the strongest correlation with class. Class describes whether a given observation represents a cancerous tumor or not. Thus, the correlation between these two attributes explains the initial insight that observations seem to be well separated by class. These insights also mean that doctors looking into whether a particular breast tumor is cancerous or not may be able to use clump thickness, bland chromatin, and single-cell epithelial size to help distinguish between cancerous and non-cancerous tumors.